outside. I just wanted to do English, but my parents convinced me. I was the one that like was really good at math in high school. So like don't do that because you'll never get a job. And then 20 years later, admitting they were probably right, but still, I could have held the line. I held the line on the Jordan canonical form. Hold the line on something else too. Okay, so I hope everybody is surviving what I'm sure now is feeling like a vice slowly squeezing in on everybody's classes. I guess I don't know if I mentioned in here, so I'm going to be at a conference next week on Tuesday and Wednesday. So I was going to offer. I already had this conversation with 304. I can have somebody come in here and teach the last couple of days. I'll be back on Thursday, and I'll be here on Friday, and then I'll be here all next week. So I can have somebody come in and teach the class on Tuesday and Wednesday as a sit-in, sort of like a sub in here, or I can teach the class synchronously and record the videos so that I give like those channels, or I can teach it asynchronously, although I don't know why I would do it asynchronously and not synchronously plus videos if I was going to do it that way. So you guys have any preference? Whoever I could manage to find. And everyone's out sick. That's really the issue. It's like 10, like something like 8 faculty members now are out. Like, I don't know if it's COVID or not, but like Linda's out and Matt's out and Camp is out. So Patton and RedSec and Camp and like everybody who I asked to sit in right now is out. And I don't know, like I can't guarantee you that it would be like my original plan for who was going to be in here. Those people are out. So I can, but that's really, I mean, I wouldn't give you the choice, right? This is not a terribly well-timed conference, but like this is one of the things I kind of have to do this. So any strong feelings about this? Synchronous? Yeah. Okay, so what I'll do is I'll do it. So the one thing I can do is I can do it synchronously and record those synchronous lectures, but I can also provide like a 20-minute sort of digest of what I was going to, I said, usually when I'm out, like when I was out sick and I was recording the short videos that covered an idea that were not like lecture style, it was more like a condensed version. I'll try to post both of those, like one asynchronous type video and then one where I do a synchronous lecture and record it, because I'll be available for those time slots. All right, and yeah, anyway, sorry, I know it's inconvenient. Just, I have no idea why people plan things this way. What's up?
So does that mean you won't have office hours?
So the office hours you should think like are gonna have, so one way to work around this is the fact that I'll probably have to like move office hours to Thursday and Friday for like, I mean, of course I'll be available remotely, right? And if I'm not actually physically at the conference, I don't know what the schedule looks like. I should be able to run the 11 o'clock office hours. And I'll definitely have office hours like in person on Thursday and Friday. And this exam is on Friday of the finals week. Right? And I promise there will be copious office hours to come talk to me during the finals week. It's been a luxury that I've got when people are, with an exam so late. Okay. Yeah, those of you that quite a few of you picked up an award last night, so congratulations for what you did at the award ceremony there. And if yeah, it was fun to see people being acknowledged for things. Okay, so where were we at on this? We need to define the following. So we're talking. Okay, let me make one more thing clear here before we get done. I have the calendar set up with a certain amount of ideas that I want to discuss, but if I cannot finish, I am not going to force the issue. So I am not going to crush us through to the end of 6C if I can't get there without like having time to understand what's happening. So I might be picking and choosing my way through the ideas as one possibility, or we just do less material than I wanted to. In either case, you're going to be fine. I just don't want to like, I know a lot of classes do this thing at the end where they go like completely nuts and it's like, oh, we have 6 sections left to go, so we got to get through it all in 2 days. Like, I'm not doing that. Okay. All right, where are we at? So we had defined last time. So I'm going to give you, we're going to start working on building up some really important ideas with inner products this time and related geometry. So I'm going to remind you that we have B, we call an inner product space. Means that B is a vector space. So it's a vector space. And it came along with an inner product. which was a function that looked like this, where you can put two things into it, and what comes out is some kind of complex number. We're talking about complex vector spaces, so it's complex. I guess really, there's no reason why we can't just put it in F here. Inner products had a whole lot of properties that make them act like dot products. We defined the notion of a norm last time, where we said, okay, well, the length of the norm, or length or magnitude of a vector, is defined to be the square root of the vector inner product with itself. And then we made the definition of orthogonal, which is we say U and V are orthogonal vectors if the inner product of U and V is 0. So sort of we're building up the basis for geometry in the abstract vector space. So we have a notion of perpendicular, we have a notion of length, and it's all built of this idea of the inner product, which remember is basically, you can think of this analogously to the Euclidean dot product, which is the inspiration for it. Okay, so the first thing that you might, the first and weirdest thing you could say about orthogonality, because it's defined in terms of the inner product, if you recall, the only vector inner product of itself that's equal to 0 is the 0 vector. If you combine that idea together with the idea that V inner product 0 is equal to 0 for all V, and 0 inner product V is equal to 0 for all V, it's not hard to see that that implies that 0 is orthogonal to everything. It seems weird. I mean, how could the 0 vector be perpendicular side of a triangle? But it's just an extension of this definition, right? If the inner product is equal to 0, we call vectors orthogonal. So the first property that comes up here is 0 is orthogonal to V for all V and V. And in fact, it's the only vector that has that property. Zero is the only vector. V. Property. Okay, so now we're ready. So we've got this basic machinery set up for some of the most important inequalities in all of mathematics. I write 3 inequalities down that I know this is linear out. Oh, whoever wrote the smiley face up there, I'm not trying to destroy happiness here, although you might feel that way. Okay, so some of the most important inequalities in every area of mathematics, not just linear algebra. The first is this one. Suppose U is perpendicular to V. Then the length of U plus V squared is equal to the length of U squared plus V squared. I know what that's called. I'm going to give it to you in letters you've seen before. C squared is equal to A squared plus B squared. It's the Pythagorean theorem, right? So the Pythagorean theorem holds in abstract vector spaces. If you want to think about what's going on with the vector picture, you think you have a vector U, you have a vector V that is orthogonal to it, and then the vector U plus V will run this way as the hypotenuse of the right triangle. So if this is the vector U, and this is the vector V, this is the vector U plus V, and as Axer points out, you almost end up feeling like you don't even need to prove it because it's a right triangle. So clearly it must be true. Length of U, length of V, length of U plus V. That's not actually a proof, by the way. I'm just pointing out this is kind of what the picture is. And the power of inner products is that you get to use pictures like this. And pictures like this can guide your intuition about what should be true and what shouldn't be true. All right. Now, I'm going to do, should I do this proof? Sure, why not? This is a fun one. Let's prove it. The length of U plus V squared. Well, I have nothing to work with except the definition of norm. Nothing. You might think to yourself, I could use the triangle inequality, but we don't have it yet. I'm allowed to. So I have to write this like this. Not even square. It's a square. Square of the norm is equal to inner product of vector with itself, right? That's the definition of length. Now what? Yeah, just chunk it up into a million pieces using the fact that the inner product can be broken up, right? So we're going to get this falls apart into u comma u plus u comma v plus v comma u plus v comma v. There would be a conjugate if I needed to flip this, but I haven't taken any scalars out, right? I have not reversed the order of any multiplications, and I haven't taken any scalars out. And remember, in both slots, it's the case that I can break just a sum can be broken up.
Wait, can you explain the process?
Sure. So first, anytime I have an inner product with a sum in one of the slots, I can break it up like this. It's linear in the first slot, right? So I can do that.
Yes.
Okay, now each one of these, there's no scalars here to factor out. Each one of these can be broken up into two inner products because I can break this into two pieces. This turns into u comma u, u comma v. That splits this one up. And then I can also split this one up, v comma u, v comma v. And notice I'm very carefully keeping the order of multiplication the same in both cases, right? Okay, anything I can do here? What did we assume at the beginning of this problem? U and v are orthogonal to each other. So what can I say? If u and v are orthogonal? Where are zeros? This is 0, and this is 0 because u and v are orthogonal vectors, right? That's the definition of what it means for u and v to be orthogonal, is that this turns into u plus 0 plus 0 plus v comma v. And now we just use the definition of distance again, or length of a vector, to say that this is the length of u squared, and this is the length of v squared. Notice this is a completely different kind of argument than the arguments we've been doing, right? These are sort of geometric, algebraic arguments using the inner product. So we're going to be seeing a lot more of this through this section. Does that make sense? I know this is not a complicated argument, but like this is thematically important. We've used orthogonality in here, and we've used the linearity of the inner product to do this. Yep.
Are we still on the theme of like trying to find?
We are the big theme that we're after here. Remember, the first big theme, the long-term goal here, is that I want to have some way of making sense of B projected onto A. Right. That's one that I want this to make sense. And then once I have this, I'm going to start talking about projection onto subspaces.
And so we suppose we are orthogonal.
Well, this is just because generally, like, if you what I want to build up to the idea here, so the short-term goal is we're building up to the idea of an orthonormal basis. We spent a lot of time talking about that in 206, right? So an orthonormal basis was a basis of vectors that were all unit vectors, which means I have to have some idea of norm, and they were all orthogonal to each other, which means I have to have some idea of orthogonality. So the entire class we've been talking about bases, but we've never talked about orthogonal bases. And that's what we're heading toward first. We're going to use these ideas to build the idea of an orthonormal basis. And then once we have orthonormal basis, we'll be set up for doing projections. So this is a first step towards working towards orthonormal basis. If you did not see that in your 206 class, you can just be like running through a field of marigolds at some point when you realize that bases can get even better. So,
When you're doing a group like that, like when it's like algebraic, if you're doing it formally, would you just say at the bottom, like above followed by?
yeah, I mean, like, yeah, you might say bilinearity. Like, you could even say like all this bilinearity of the inner product.
You want to like break it up?
I mean, you could, I guess, line by line do it. If you were doing it for me on an exam and you did exactly what I wrote here, I would be totally happy with that. You know, on the homework, if you get jammed up on the homework, which, you know, I'll tell them to kind of go easy on this stuff, right? Line by line justifications of these things. We're sophisticated now. We're the end of 306, not the beginning, right? So as sophisticated writers of mathematics, which you guys clearly are, this is completely, if you do this, you'll have convinced me that you know what's going on. You don't need line by line justifications of simple like operations with the inner product. Okay, so now that is one. This is sort of our like one of the most important sort of geometric identities here is that if U is orthogonal to B, and the length of U plus V, length of U squared plus the length of V squared. Now I'm not going to prove the next one, but I suggest that you do. The first thing we're going to do, though, before we do that, is finally we're ready to define this thing formally. We're ready. We've got all the pieces we need to make that make sense. And last time what you guys told me is I should just use the same theorem I already had for regular old Rn, but put inner products into it instead of dot products. That was suggested to be the right idea. And indeed, that's what we're going to do. So we're going to suppose that U and V are not zero vector. And then we'll let C be this quantity. U, V, I have no idea why Axler does this, but I'm going to put VV right here. What Axler says, he defines it this way. V over length of V squared. It doesn't matter. It's the same quantity, right? V comma V and the norm of V squared are the same thing. Matter of taste, I suppose. Then, set the vector W to be equal to the vector U minus UV. Why the hell does it go through the process of giving us the name C and then not using C? What a weirdo. Sorry, Sheldon. Okay, so really what he means here is this is C minus C. Right? He just defines this quantity C. Does anybody remember what this is called from Math 206 and Math 241 and Math 143 and pre-calculus and physics? It's the scalar projection of B onto A is what that's called. Almost. Anyway, yeah, you've learned this like 9 times, right? What this object is. But now we're doing it with an abstract V instead of Rn. We're sophisticated now. Okay, so we define this thing that somehow measures how much of U points in the direction of V. That's a way of thinking about what C measures. And then W takes U and subtracts off C times V. This guy right here, that's called the vector projection of U onto V. Again, you've learned these before. They're not as mysterious as they look. The conclusion of this definition is these vectors are perpendicular to each other. And U is equal to CV plus W.
Can you draw a picture?
I'm going to draw a picture right away. Now the picture is going to lie to you because I'm going to draw you a picture that represents R2. And then you just have to pretend, like every working mathematician, that every vector space is R2. So here's the picture. This is the vector we're projecting onto. This is V. And up here is the vector U. All right. So this is V and this is U. The length, okay, so poking in this direction V down here, there's a unit vector, a vector of length 1. How can I make V into a vector of length 1? Divide by its length, right? So down here, this is V divided by the length of V. That's this little vector. Then I compute the length of this vector. And the length of this vector, so this length right here, maybe I'll put the length of this guy, length is equal to U comma V over the length of V. So when you put those together, that's where C comes from.
So wait, so C.
So
Wait.
this thing right here is a unit vector pointing in the direction of V.
Yeah.
And if I multiply it by the length of the projection, I get this vector.
So you have length in directions.
Yeah.
Then where's the V?
Where's the W?
No, like the V, if you multiply that.
This vector, okay. This vector out here, this long vector is V.
Yeah.
This is CV. CV is the vector that looks like this.
Oh, so C just like a scalar.
C is
part?
the scalar part of the vector that points in the same direction as V, but is the image of U.
Oh, okay.
And this vector is W. So what we're saying is if you do CV and then W, you get U back again.
Okay.
Again, for those of you that have seen this picture 900,000 times, I apologize, but it literally is the same picture. Okay, now this idea that we can take one vector and project it onto another one is pretty important. And the core of why linear algebra is even useful. So let me make this more clear by writing, like formally saying this, because I think Axel doesn't say this at this point. So in this setup, the vector CV is called the orthogonal projection of U onto V. Right, that's probably appropriate to our class to call it that. So this vector CV right here, another way of thinking about it, it's the image of U in the direction of V. All right, so now this one I'm going to give you to read because this is one of the super important theorem and also a kind of a key proof. So this one is the second of the major inequalities, or the second of the major sort of equalities of vector calculus and all of analysis from it. This has a fancy name. It's called the Cauchy-Schwarz inequality. If you get up into 412 and 413 and 414 and you take graduate analysis, you're going to feel like your entire life is just applying this over and over and over again. Like you might think like what I do for a living is apply this. So let U and V be elements of V, then the length of the inner product of U and V is less than or equal to the length of U times the length of V. And when I say length here, remember UV is a number, right? This is a number that comes out here. And I take its absolute, it might be a complex number. So this is like the absolute value of a complex number. It's the length or magnitude of a complex number. What we're saying is, whatever this number is, it's smaller than the individual contributions of each of these vectors. Okay. So it's a way, so you might think like, what the hell is the point of something like this? Why would we do this for? So this is sort of where we get into a type of mathematics that is non-algebraic. This is what's called an estimate. In a lot of higher types of mathematics, the idea is you can't be exact anymore. But if you can show that things are smaller than things, you get the results that you want. So you lose specificity. You might not know exactly what this number is, but you know it's controlled in some way. So analysis, so 412, 413, 414, 408, 409, any of the numerical classes are built off of ideas like this.
Does it matter if you use double size?
If you use what?
The double.
It does. Now the reason that it's okay, so there's an important point to make here is why do they use single bars on this side? What kind of object is U comma V? Complex number. Complex numbers have absolute values, or it might be a real number. Real numbers have absolute values, right? So absolute value is there because this is a number that you're taking like the double bars here mean this is the norm that comes from the inner product. So this is the length of a vector, and this is the size of a number. That's why we use the one bar on one side and double bars on the other. Okay. Yep.
And then what is that last line?
Oh, right here?
Yeah.
Then, so you go through this setup and you build the pieces. This says the inner product of V and W is equal to 0. And also the original vector U is equal to CV plus W. So what we're saying is these vectors are orthogonal to each other. CV and W are orthogonal. And if you add CV to W, you get U back again. So it's not just that CV plus W is equal to U, it's also that these are perpendicular. Okay, so what I would like you to do, I would like you to read this proof. is not a hard proof, but it is very like illustrative of the way this stuff works. I want you to stare at it because there's going to be double bars running all over the place and numbers moving in and out of norms. And I want you to grapple with what this argument looks like. Not complicated, but the idea of moving numbers in and out of norms is really important. So I want you to go line by line. We'll talk about this next time. I want you to go line by line and make sure you can understand what the algebraic steps happening from line to line, because proofs like involving this inequality are going to look like this. Okay, and the last and third and possibly single most important inequality that's ever been invented in any field ever. What I call in my analysis classes the hammer of analysis. And why do I call it the hammer of analysis? Because there's an old phrase that says when all you have is a hammer, everything looks like a nail. Every analyst, the very first thing you do when you see a problem is try to hit it with this inequality. There's a hammer of analysis. Not an official name, it's my name for it. I'm going to call it the hammer of analysis. Most people who are normal call it the triangle inequality. And then I'm going to say why it's so important. Here's what it says. So we've got active language here. Okay, let U and V be in V. Then the length of U plus V is less than or equal to the length of U plus the length of V. So why? Why is this called the hammer? Why do I call this the hammer of analysis? Now, this is not the Pythagorean theorem, right? The Pythagorean theorem said that you have U plus V squared is equal to U squared plus V squared. That was only true when U and V were perpendicular to each other. The power of this is it always works. You put any U and V in here you want and you get this inequality. So what's the point? Why do we care? What could possibly be so important about this? Why am I spending 5 minutes trying to exhort, or extol the virtues of the triangle inequality? Probably all of you guys have done this in the past, right? You've been sitting around on a calculus exam and do some annoying calculation and somebody wrote down a squared plus b squared and you look at it and say, man, it sure would be nice if I could distribute that square root. And then you do something called the freshman dream. It has a Wikipedia page. It's called the freshman dream. What the freshman dream says is, well, then just do it. Why not? Just do it. Okay. Totally false, by the way. I'm sort of embarrassed that this is on video, right? That this is totally false. Again, you go ahead and if you want to amuse yourself, you go look at it. I was quite pleased to see that this is posted as a freshman dream. Okay, but the idea is, man, that sucks that I can't do that, but you can as long as you're willing to use a less than or equal sign, right? All those annoying computations where you've been tempted to do this in the past because you just didn't see how to simplify the square root sign. If you're doing analysis or vector calculus and you say to yourself, man, it is lame that I can't take this it's lame that I can't take that and spread the square root around. Except you can. That this thing is less than or equal to the square root of UU plus the square root of VV. This is in the sense in which this is sort of a freshman dream-like argument, right? This is incredibly useful. If you were making fun of analysts, you would say this is all the field is figuring out how to apply it. And I am an analyst, and I would still characterize it that way. Okay. So again, and to reiterate, the three sort of big dog, now we've got three big dog theorems. The one is if U is perpendicular to P, then we have U plus V squared is equal to norm U squared plus norm V squared. The second one is for any U, V, and V, we have the absolute value of the inner product of U and V is less than or equal to the length of U times the length of V. The third one, for any U and V in V, we have that the length of U plus V is less than or equal to the length of U plus the length of V. And as there's no avoiding the fact that at some point inequalities become the language. There's just nothing else to do. You want to be exact, go be an algebraist. 4. What's that?
It's 2 and 3. They're not similar.
So you have to have 2 to prove 3. So the proof of 3 actually follows from the Cauchy-Schwarz inequality. So I'm assigning you, so I assigned you the proof of 2. I'm also assigning you the proof of 3. Again, because these are important proofs to have gone through. You should read, this is the place where you should really engage with the book and read these arguments. They're not complicated, but they are extremely revelatory about how this math works as you keep going with it. And why we even introduced the idea of inner product at all. Okay. So yeah. Like I'd be really curious to see talk to you guys in a couple of years after you've taken analysis and you realize like really it's all it is like when I was in analysis, Patton got mad at me one time and told me that at some point she just expected every homework exercise to be me writing down the triangle inequality as my answer in the analysis sequence, which was fair, but like on the other hand, once you figure out the central idea, you guys do this in here sometimes too, like, okay, I figured out why the problem works. I just want to write that part down and nothing else. So I got in big trouble for that. When I was an undergrad, and Paul likes that story so much, he was yelling at his graduate students about them doing what I did. He used me as an example of what not to do. That was a long time ago, and I've changed the error of my ways. Okay, so these things have to be worked with. They have to be worked with. You got to do examples. Really, when you're doing the homework in here, work with these things directly. Don't cheat yourself. This is one place that manipulating these things is so central to what it is to be a mathematician in any area, like abstract, discrete, applied, pure analysis. Like, don't go to linear algebra. Okay, nobody knows that linearalgebra.com exists. But if you do, don't go to Wikipedia and look up how to do these. Don't go to Stack Exchange. Don't go to Math Overflow. Don't go to the defunct corpse of Yahoo Answers. Don't go to linearalgebras.com. Don't go to Chegg. Don't go to the Chegg solutions to the entire linear algebra book that are posted there. Don't go on Reddit. Do these. Like, seriously take the time to try to work these exercises. And I'm sure, there are other resources that I'm leaving out here that I also know exist, but I'm trying to give you the idea that I know they're all out there. So anyway, yeah, don't cheat yourself. This is a place where it's worth doing this. I know we're sort of at the end of a quarter and everyone's tired, but like, work you put in here is going to carry through in other classes. Okay, so now what the hell was the point of all this? So fine, we spent all this time, and Tully Doyle told us that these were really important for analysis, but we're doing linear algebra. What the hell does that have to do with anything? Okay. So I want to know. We spent all this time building up all this. I keep calling it geometry. Why? Why do I even care about an orthonormal basis? I told you orthonormal basis. So, what would be really nice about a basis of vectors? Or like, what? Does anybody have any idea why we're doing any of this? Oh, fine. You cooked up a thing called the dot product. Ooh. I mean, sure, I told you the long-term goal was to think about things like projection and whatnot, but so what? Why are we doing any of this? The coordinates are nice. The coordinates are nice. That's true, but I don't even need coordinates yet. And we will get coordinates eventually, I suppose. Okay. So yeah, so we've got coordinates on the page. We got the idea of like being able to compare vectors in terms of like introducing a notion of magnitude. But like, so what? Yep.
It seems like cleaner to be able to represent a vector as like a linear combination of orthonormal vectors.
Well, what should an orthonormal vector be? That's the first thing. Like, what should we demand? So we've got two really different sets of ideas running around right now, right? We have all the stuff we did from chapter 1 to chapter 5, which basically focused on subspaces and bases, right? All that stuff in chapter 5, all of it. I'd say chapter 1 up through chapter 5, the main focus has been on subspaces and basis. Even the eigenvalue and eigenvector stuff was really focused on this, right? It's a special kind of basis and a special kind of subspace. We spent all this time talking about subspaces and basis. And now, all of a sudden in chapter 6, we stop and take this left turn and somehow say, I guess, travel in an orthogonal direction. And all of a sudden we introduce this idea of norm and orthogonality. Both of which we got by looking at inner products. How are we going to mix these together? What should we demand from a basis? What would be the nicest possible way a basis could show up? I mean, we already know what is a basis. There we go. There's a test question. What is a basis? I told you to put that tattoo in your brains. What's a basis?
Set of vectors of the linear independent spans.
A linear independent spanning set. Sweet. Okay. But it could be more than that. A basis could be more than a linear independent spanning set. What if I wanted an extra good basis? And I said, well, why can't I just divide them all by their lengths so that they're all a unit vector? What would happen in the projection? Remember, in the projection formula. So think about the projection formula for a second. If you calculated the, like, so what we wrote down is the projection of U onto V, U dot U comma V over V comma V, V. Or if I like to really emphasize here, the length of V squared. If V was a unit vector, what would that be? 1, oh man, that would make things nice, right? Because then I could compute projections just by doing that. If I had unit vectors that I was projecting onto, this wouldn't be there, right? So maybe I could project, so the long-term idea here is maybe I can use the basis to project onto. And if they were unit vectors, there would be nothing in the denominator of these fractions, which would be really nice, right? So maybe I should demand, what if I took a basis and I said, I want a basis, but also, I want it to be unit vectors. That'd be cool. But I could demand more. What if there was a way of taking that? Now, it's easy to see how to take a basis and make it into unit vectors, right? You just take a vector and you divide by its length and you get a unit vector. The length of a vector divided by its length is 1. And man, it'd be extra nice. I mean, you spend all this time, your whole life, talking about R2 and R3, where the basis vectors are like this. X, Y, and Z vectors are in this frame where everything's perpendicular to everything else. In the XY plane, we never use anything other than 1, 0, and 0, 1 as the vectors, right? Those vectors are not only unit vectors, but they're orthogonal to each other. If you guys took 241 or you took 304, you've seen the TNB frame, right? Where you calculate the tangent, normal, and binormal vectors. And those are orthogonal unit vectors. If you haven't seen that before, it's in your future probably, right? But the idea is most of the examples that you've seen of working with coordinates in the past demand not just that the vectors are unit vectors, but they're like the X and Y coordinates, the IJK vectors from 206. They're perpendicular to each other. So the extra bonus feature would be if somehow we could also demand that the basis was an orthogonal basis. Maybe I could demand that these things act like the X and Y coordinate vectors. The X and Y coordinate vectors are perpendicular. Well, that's what we're going to do now. We're going to look at a way of combining the idea of a basis from chapter 1 through 5 with orthogonality, and we take that basis and turn it into an orthogonal set of vectors with the same span. So it's like we're somehow straightening the basis out. And then we're going to like divide by all the lengths to get unit vectors. So the goal here is to make a basis, but even better. Okay. That's the project of the next part of the class, is to come up with an idea of really nice notion of basis.
Why do we want this basis again?
So it turns out to be the case that the long-term goal here, there's a theorem from Math 206 I'm going to write down right now. So in Math 206, you learn the following. If you have, say you're in Rn, so you have a vectors in Rn. So the 206 theorem we're trying to recover here is, if you were in Rn and you had V1 up to Vn of basis, say an orthonormal, a basis of orthogonal unit vectors. So if you started with a basis and they were orthogonal unit vectors, and you gave me any other vector you wanted, you just write some V down, right? And then I say, tell me the coefficients that go in front of, I mean, this is equal to C1 V1 up to Cn Vn. And up to this point in this class, we've had no way of telling what C1, C2, C3, C4 up to Cn are, right? We don't know. We've never seen a way of actually computing C1 or C2 or C3. I mean, V1 through Vn is a basis. So any vector V can be written as a linear combination of that basis, right? If these vectors are orthogonal unit vectors, one of the biggest theorems of Math 206 says is that V is equal to the dot product of V with V1, V1, plus the dot product of V with V2, V2, plus the dot product of V3, V3, and sorry, V with V3, out to the dot product of V with Vn, Vn. There's a computation formula that tells me what all the C's have to be. They're unique coordinates. So this is a coordinate computing theorem. If you started with a basis that was orthogonal unit vectors, you can tell me what the number that goes in front of the V1 must be. It's not just some arbitrary C1. You know exactly what that number has to be. So what we're trying to do is we're trying to figure out a way to take this theorem, which was a theorem of Math 206 of Rn, and sort of build it back up again in an abstract setting with inner products instead. I would love to be able to just compute the numbers that go in front of a linear combination, right? From a computational perspective and from a pure math perspective, this is about the most efficient thing you could possibly ever cook up in linear algebra. It would be a fast way of writing these numbers down. You come along and say, like I say, I've got an orthonormal basis. And you say, oh, fine, tell me what this vector is expressed in that basis. You could just do it. This is how computers do it. Sometimes.
So this only works on the basis of orthogonal.
If they have to be orthogonal unit vectors to work. So in 206, the big point here is you spend tons of time talking about, in fact, I'm going to try to, like, hopefully I don't scare anybody away here, but there's this process called the Schmidt process that you would have learned in Math 206, which had to take a basis and shave it apart until all the pieces were perpendicular. We're going to do that, but in an abstract setting. So we're going to take, I want this theorem that only works with orthogonal unit vectors. I have to figure out a way to take a basis and make it into an orthogonal basis so that I can use this theorem, right? So I want this theorem. This is like the cornerstone theorem of like this kind of linear algebra. This is the most useful computational formula that you can find with respect to basis. Because now it's not abstract anymore. I could just tell you the numbers. Okay? And we don't have this theorem yet because, I mean, I haven't told you anything about how, like, the basis, what an orthogonal basis does and how to make sure that the span is the same and, like, even what an orthogonal basis is. I haven't told you any of that, but I'm trying to, this is a heavy enough lift that I'm trying to, like, really nail down the analogy with Rn. The beauty of the inner product is it lets us basically recover all of the theorems of Rn. This is one of the biggest theorems of Rn. If your class got here, I think most 206 classes get there, but not all. Yep.
I have another question. I can see how, like, when you explain that the basis can be reduced down to a unit vectors basis, but if you try to make that set of vectors, like the basis set of vectors, to be perpendicular to each other, will you change the basis?
Oh, so this is the central question: is how do I make vectors orthogonal without changing their span? Is what you're asking.
Yeah.
And the answer is a super beefed up version of the Schmidt algorithm, which means I basically, to remind you guys, I'm just going to say this in words. Maybe I can remind people how people's memories work. What you do is you start with a vector and you say, okay, take another vector, build that orthogonal decomposition that we talked about, where the CV and the W. Figure out which part of V2 is perpendicular to V1, and then throw the rest of it away. Then you give me a V3 and I say, figure out the part that's perpendicular to V1 and also the part that's perpendicular to V2 and throw the rest away. And then you've got 3 vectors that are perpendicular. So every vector you get, you have to figure out the pieces that are perpendicular to everything that came before. So you just project over, and over, and over and over again. And when you're done, everything's orthogonal, the span is the same. But you should not believe me, by the way. This is a thing that requires proof. I'm just telling you kind of where this goes. Right? This is a super important question, how this part works. That part is easy. This is not. So if you want to read ahead for next time, the page to do it on, I will point it out. 6.31, the masterpiece called the Graham-Schmidt procedure. The Graham-Schmidt procedure is so nasty that when mathematicians do it, they just say, assume the basis is orthogonal by a Graham-Schmidt process. In theory, any basis could be orthogonal, so just assume you have an orthogonal. Nobody actually computes an orthogonal basis. 6.31. So this would be, so the reading for next time should be the top of 6b, which starts with the definition of what it means to be orthonormal. How to write, in fact, this formula is 6.30. This formula right here that we really want, this formula is 6.30. And the justification for the fact we can always work with an orthonormal basis is 6.31. And the only reason I'm not going into more detail is because it needs more detail than I can give it in the so I'm trying to give you an overview, because this is, again, there's like sort of a pretty big change in the way this stuff feels. All right. So I guess I'm gonna finish up. There's a really, so one thing I will tell you is if you read chapter 6, you don't have to go past 6.35. I'm not going to put a lot of emphasis on the upper triangular matrices, at least for right now. I really just read up from 6.30 to 6.35. There's stuff at the end about a theorem called Schur's theorem, which is awesome, but I'm not going to teach. And then the idea of linear functionals, which is really sad because that's what I do. I'm a functional analyst, and what we study is linear functionals. And I'm not sure that we're gonna be able to do that, but someday in your life, this stuff will be like really important, just not quite yet. It'll be done more justice in a future class. And then what I'll do, so take the time and really like wrestle with this stuff, because in a very real way, this is the entire point that justifies abstract linear algebra, is that we can do this.